Okay. So, good morning, everybody. Good morning, good afternoon. And it's an honor and a pleasure to present Alessandra Celletti. She is a full professor of the Department of Mathematics of the University of Roma Tor Vergata. And she's very active in scientific societies, editors boards of important journals of the area, in particular celestial mechanics and dynamical astronomy, and works also in supporting women in science. So she is, as everybody knows, is very active in dynamical systems and celestial mechanics, in particular Tkm Theory and applications. And I'm sure that it will be a pleasure to listen to her. And as last year in in CBDO, it was a very nice talk. And today won't be different, I'm sure about that. So, Alessandra, it's a pleasure to listen to you.
Thank you. Thank you very much for this introduction. So let me say that first say that I thank you very much for giving me the opportunity to present the results today. They are completely different from CBDO because while in the past talk I was presenting something with applications to space debris, now I will keep something of celestial mechanics because I always need to see something moving in the sky. But from a more theoretical aspect, that is that of Tkm theory for dissipative systems. So let me start to share the screen. So can you please confirm that you can see my screen?
Yes, we can see your screen.
Okay. So the subject of this talk will be indeed a Tkm theory for a dissipative problem of celestial mechanics, which is called the spin orbit problem with tidal torque. We have today experts in both fields, Tkm theory and also celestial mechanics, and in particular the very famous experts in tidal theory. I want to just to say that this will be a very simple model, a prototype problem without any, let's say, any claim on the physical situation. So I will not go into details of tidal theory. This is a joint project in collaboration with Renato Calleja, who is attending the talk, J.Gimeno, and Rafael de la Llave. And we started some years ago, a couple of years ago, and we are now just finishing the third paper of this series. And this talk will refer to these three papers. The first two were published last year, and the third one is ongoing. So, but first let me start with an introduction. And okay, so this is a typical timeline of celestial mechanics from ancient times to more modern times. We see here that we start modern celestial mechanics with Kepler, the study of the two-body problem, well beyond the discovery of gravitation by Newton. And we will be mainly concerned to theories developed in this last part of this timeline, and precisely perturbation theory, and more recently Kolmogorov Arnold Moser theory and Nekoroshev theorems, which give information about the stability of nearly integrable systems. So why perturbation theory is effective in celestial mechanics? We can start the study of any problem of celestial mechanics, starting with the two-body problem. For example, the motion of the Earth around the Sun, which is known to be integrable, which is the solution is given by Kepler's laws. And it can be described by a simple Hamiltonian function, which in action angle Delaunay variables, it depends just on the action. So this is an integrable system. And when we pass to the three-body problem, for example, the Earth under the gravitational attraction of Sun and Jupiter, we end up with a non-integrable system, but nevertheless, it is a three-body problem is a nearly integrable system in this case because it can be described as the integrable part, the Sun-Earth Keplerian part, plus a perturbation due to Jupiter, say epsilon. Epsilon is a small parameter which amounts to the Jupiter-Sun mass ratio, which in reality is 10 to the minus 3, and then a perturbing function which represents the gravitational interaction with Jupiter. So we know since Poincaré that this problem is non-integrable, but perturbation theory can help to find an approximate solution. And later Km theory can help to prove the existence of quasi-periodic motions, and Nicolai's theorem to provide stability over exponential times. So why is perturbation theory important in celestial mechanics? I want here to underline two aspects. On one side, it is very, very effective. On the other side, it is very complex. And the examples that I usually borrow are from the 19th century, both are from French people, Le Verrier and Delaunay, because in 1846, Le Verrier discovered the planet just with pen and paper. At that time, Uranus was the last planet known, but the scientists were well aware of the fact that there were discrepancies between the theoretical prediction of Uranus and the astronomical observations. So Le Verrier had the idea to conjecture an extra planet which placed at the right distance and with the right mass could justify these discrepancies. So he made computations with using perturbation theory. He made these computations and he placed this extra planet within a range of only 5 degrees. He sent his computations to an astronomer in Berlin, Gall, who got the letter on the same day. He observed the sky and discovered the planet Neptune. So you can imagine how effective was, since that time, perturbation theory. On the other hand, perturbation theory is also quite complex, and the example that I borrow is that of Charles Delaunay, who implemented perturbation theory to compute ephemerides of the moon. And he spent 20 years of his life to make these computations. There are two books which are in Rome. We have the historical library at La Sapienza, and I was lucky to get these books at the time of my master thesis, to bring that at home. Now it is not more possible because they are classified as historical books, and read them. These two books, of each one was 1,000 pages, and which contained all the computations to give the position of the moon, the ephemeris of the moon. And why Delaunay spent 20 years of his life is well understandable from looking at the first pages of his book. In the first pages, he gives preliminary computations, and then he starts to provide the Fourier-Taylor expansion of the perturbing function in terms of the orbital elements. What do I mean? The Taylor expansion in terms of semi-major axis eccentricity and inclination, or sine of the inclination, and sine of half of the inclination, and the Fourier expansion in terms of the mean anomaly, argument of perigee, and the longitude of the ascending node. And the resulting function that is the starting point for perturbation theory is given here at page 33. It continues at page 34, 35, 36, and that's up at page 54. So we have 22 pages just for the starting point, after which Delaunay implemented perturbation theory. Then Desprez made some computation, the check with the computer at the end of the 60s, and found just a couple of mistakes in unessential coefficients. So the reason why I wanted to give these examples is to underline that perturbation theory is very effective and it is complex. So we can use perturbation theory and later Km theory or Nicolai's theorem, as I was saying at CBDO, to provide results in physical problems, and we can provide effective results, paying the price that the computations become complex and therefore we need to use a computer. Which are the recent applications so far? In recent years, these are just recent years, There are many computations based on Km theory, normally hyperbolic invariant manifolds, Nekorov theory, perturbation theory, and this is a list. Invariant manifolds for space trajectories by Anderson from JPL, Kumar and Llave from Georgia Tech, or use of normally hyperbolic invariant manifolds in satellite theory by Tkm, Eftimiopoulos, Kollias, Rosengren, and co-authors. Very recently, with de Blasi and Eftimiopoulos, we implemented perturbation theory and Nekorov's theorem in satellite problems. And in a very recent paper, 2 papers indeed in scientific reports and in celestial mechanics with Pucacco and Tudor Bartolomei, who is a PhD student at Roma Tor Vergata, we computed the so-called proper elements, so integral, quasi-integrals of the motion for the full system, to backtrace space debris and to reconnect space debris which are left in the sky to the object that originated such debris. So now, after this introduction, I want to go more in depth into Km theory for these dissipative systems, which are called conformally symplectic systems. And to do this, I start with a simple example, simple pictures, which are nothing but the well-known standard map. So it is a 2-dimensional map on the cylinder with variables x and y. And depending on a parameter epsilon, and for epsilon equal to 0, the map is integrable. The map is integrable, and we take here 20 different initial conditions, each one corresponding to a different line with different colors. So this is a quasi-periodic torus for this initial condition for the case epsilon equal to 0, the integrable case, and we have 20 different invariant tori, so rotational tori spanning the whole range 0 to pi in the integrable case epsilon equal to 0. And we know that Km theory tells us is a theory about the persistence of invariant tori when we switch on the perturbation. And when we move the parameter, and this will, as we will see in a moment, the theory is developed both in Hamiltonian and in dissipative non-Hamiltonian systems. But let us see now what happens when we switch on the perturbation. We see here the case epsilon equal to 0.3. The system is no more integrable. There are no, some of the tori are replaced by periodic orbit here at the center, and then librational tori. And when we increase the perturbation, we see that there are left less and less invariant Km rotational tori, which are replaced by librational tori, smaller, higher order librational islands, and chaotic motions. And then we reach a threshold, and we are very much interested to this threshold. The threshold at which we are sure that there are no more invariant tori. And this threshold is indeed very close to this number 1. It is a 0.971. This is a magic number for the standard map. At that point, just for simplicity, I just approximate it with 1, but it is a 0.971. At that point, there are no more invariant tori. And indeed, the last torus, if we go back at the last torus, which disappears, is that with frequency equal to the golden ratio, which is the best irrationals among all irrational numbers in 2 dimensions. So this is the situation in the conservative case. The standard map is a symplectic map, so the Jacobian is equal to 1. It is twist in the sense that dx prime over dy is greater than 0. And the theory was originally developed by Kolmogorov, Arnold, Moser in the Hamiltonian setting, but it was soon extended by, for example, by Moser in Mathematician Allen in 1967 to general and dissipative systems, and later there are very nice mention that the theory holds provided that one introduces some extra parameters. So one needs extra parameters which are needed to be adjusted in order to find the tori. In some sense, one needs to insert, to push inside some extra energy so that the tori persist. What we did in the first paper of our collaboration with Renato Calleja and Rafael de la Llave, published in JD in 2013, was to develop again Km theory for a special class of dissipative systems, which are called conformally symplectic systems, paying attention to find efficient Km theory. So providing estimates giving estimates which provide results in agreement with the numerical or astronomical expectation. So once again, let me remark that the dissipative case is quite different from the conservative one, from the Hamiltonian one, because while in the Hamiltonian case, we saw that we are plenty of invariant tori. We had at the beginning, we had 20 different initial conditions. When we switch to dissipative system, you have just few attractors. And you need to let the system evolve to end up on the attractor. You need to include these extra parameters, which are called the drift parameters. In both cases, Hamiltonian and dissipative cases, the Km theory can be developed under these main well-known conditions, which are the fact that the frequency of each of these invariant tori should be Diophantine to deal with the so-called small divisor problem. And also it has to be satisfied a suitable non-degeneracy condition, either in the Hamiltonian, a different one in the dissipative case. And this will ensure that suitable cohomological equations can be solved and can provide the approximate solutions. So why are we interested to conformally symplectic systems and to dissipative systems in celestial mechanics? Because many problems of celestial mechanics are indeed modeled by a nearly integrable Hamiltonian. We saw the three-body problem, which is a two-body problem plus epsilon times a perturbing parameter times a perturbation, which makes it a nearly integrable system. But we also have several examples of problems of celestial mechanics, which are nearly Hamiltonian. That is, they are not conservative, they are dissipative, but with a small dissipation indeed. So we will need to consider near Hamiltonian functions with conformal factor lambda, which measures the dissipation, and the drift parameter mu, which is, as I said before, needed in dissipative systems. We have plenty of examples. I will deal with the spin orbit problem with tidal torque, but we can also mention the three-body problem with Poynting-Robertson, Stokes drag, which are dissipative effects, or just solar sails when the sail is oriented in such a way that there is a dissipation from the solar radiation pressure and so on. So let me show in this movie what happens in a dissipative system. So again, so let me start first explain what I want to say now. I want to give a movie in which we move the parameter epsilon, but now for a dissipative system, which will be the dissipative counterpart of the standard map. So it will be a dissipative map. We, instead of saying that it is conservative, we prescribe that it is a dissipative system with the rate of dissipation equal to lambda. Then we take again 20 different initial conditions. We wait for a transient time because we are in a dissipative system. So we make some iterations, and then we plot, after this number of iterations, we plot the final result where once we know that the system has landed on the attractor. And then we move the parameter. For each of the values of the parameters, we do the same. We take 20 different initial conditions, we wait for the transient time, and then we plot the attractor. And the movie is the following. When epsilon is close to 1, we are close to the line, which is a quasi-periodic attractor. In a dissipative system, there could be just one quasi-periodic torus. There could not be two tori, otherwise the region in between would be preserved. And then we increase the parameter, we see that the torus is distorted. There is a periodic orbit here, this dot here, another periodic orbit here, more and more distorted as we approach a critical threshold at which it disappears and leave place to just two periodic orbits. So as maybe you notice it that the critical threshold was close to 0.98. In the conservative case, it is 0.97. In the 971, in the dissipative case, it is a number close, different, but close to between 97 and 98. So this is the situation in the dissipative system. And as I said before, we have examples from the free body problem, the spin orbit problem, which are nearly integrable Hamiltonian systems plus dissipation, and in particular the spin orbit problem has a dissipation which is linear in the velocity. So it makes this system conformally symplectic, as I will see according to the definition I will give in a moment. Now, why do we want to implement Km theory? Because we want to have a constructive algorithm to give this existence, to give a lower bound on the perturbing parameter epsilon, so that we can say that for epsilon less or equal than this analytical threshold, epsilon Km, depending on the frequency of motion, for example, the golden ratio, for epsilon less or equal than this threshold, there exists a Km torus with frequency equal to this frequency omega. And then the main question that led most of my studies in my life is, does Km theory provide realistic estimates with results consistent with the experimental value? So first of all, what is the experimental value? We can either say the astronomical value, or rather, we are happy if we are able to prove results for the three-body problem for epsilon equal to 10 to the minus 3, the Jupiter-Sun mass ratio. Or rather, if we are in a system like the standard map, then we don't have a physical value, but we have a numerical value, so an experimental one. So we have an astronomical value, which is typically less than the experimental one. But nevertheless, the question is Km theory able to give results for epsilon Km about equal to the astronomical, or even better, the experimental value? Okay, this was the question that on which, let me say, I worked much more than Delaunay did, much more than 20 years. Now it makes almost 40 years. 40 years this year. No, 40 years in 2 years. Sorry. So of course, I'm much slower than Delaunay. So, and the question is that thanks also to the collaborations with several co-authors, starting with Luigi Chierchia, then Corrado Falcolini, and then in recent times with Renato Calleja, Rafael de la Llave, and J.Gimeno, we were able to find results which are very much in agreement with the experimental value. And therefore, let's say that we are able to give a positive answer, even though in the 60s, it was given by Michel Hennon, a first estimate, showing that the epsilon Km was much smaller than the astronomical observation. But as you know, this computation, which was done by Michel Hennon, was contained in one page of a letter addressed to Arnold. And by the way, Hennon was himself aware of the fact that the computer could help to find much better estimates. This was according to a conversation I had with him once I was visiting the observatory in Nice. So what do we implement? We implement to find these realistic estimates. We implement the so-called a posteriori approach to prove Km theory. The posteriori approach was introduced by Rafael de la Llave in his book, and later in a paper with de la Llave, with González Jorba Villanueva, and it is based on the following two main steps. Reduce the existence of invariant objects to find solutions of a suitable functional equation. And then if you have an approximate solution which satisfies some non-degeneracy conditions, then you can prove that near such approximate invariant solution, there is a true solution. And this is obtained by means of a Newton's method and proving the convergence through smoothing operators, so using a Nash-Moser approach. The advantage of the approach, which is the posterior approach, is that you don't need to have nearly integrable systems. You do not need even to use action angle variables. So now let me introduce conformally symplectic systems. So let me say that this is the formal definition. Let me say that, let me start with a manifold M, which is a symplectic manifold endowed with a symplectic form capital omega. Then we say that the diffeomorphism F mu, like the standard map from M to M, in that case R times T to R times T, is conformally symplectic if there exists a function lambda such that the pullback of F mu applied to omega is equal to lambda omega. And you immediately recognize that this definition becomes the symplectic condition if we take lambda equal to 1. Now, for d equal to 1, any diffeomorphism is conformally symplectic with this lambda, and it is easy to show just by taking the exterior derivative of this expression here, that in dimension greater than 2, lambda must be a constant. Then we can also extend this definition to flows, to continuous system, and we can say that a vector field x mu is conformally symplectic if it satisfies this expression here. That is, that the Lie derivative Lx mu applied to omega is equal to lambda omega. And this means that the time t flow phi t satisfies a relation similar to the previous one. That is, phi t star omega is equal to e to the lambda t times omega. Well, for simplicity, I will just give results for the mapping case, but of course, we can also extend. I want to stress that all results can be extended also to the continuous systems. Now, the definition of the Diophantine condition for mapping systems, we need to divide, normalize by 2 pi, and say that the frequency omega satisfies the Diophantine condition if omega over 2 pi times q minus p to the minus 1 is less or equal than a Diophantine constant c times q to a Diophantine constant tau, where q is a vector in ZD, not 0, and p is an integer. And we know that the set of Diophantine vector for tau greater than d minus 1 has full Lebesgue measure in RT. And finally, we need the norms. We need the norms because we want to give explicit estimates. And I want to stress that since the first paper in 2013 with Rafael and Renato, we developed all the theory either using analytic norms and Sobolev norms. This is very important for what I'm going to say for the last part of this talk and for the ongoing project that we are just finishing now. So analytic norm means that we introduce the extended torus, that is TD rho is the set of theta complexes such that the real part is in the standard torus TD and the imaginary part is bounded by this coefficient, positive coefficient rho. And then we take the sup of f of theta over TD rho, and we define this analytic norm. Then the Sobolev norm, we expand in Fourier series the function f. We introduce for an integer m, we define the analytic norm in this way through the Fourier coefficients of the function. This norm will be very important to find the numerical, the experimental breakdown threshold of the invariant tori, while we will use the analytic norm to prove the existence of the invariant tori through the theorem. So what is now the definition of the Km tori for conformally symplectic maps? Well, for a family of mu, depending on a parameter mu, of conformally symplectic maps, we say that a Km torus with the Diophantine frequency omega is a d-dimensional invariant torus which is described by an embedding K and a drift mu, which are solutions of this invariance equation. F mu composed with k of theta is equal to k of theta plus omega, which means that in these parametric coordinates, the flow is linear. Parametric coordinates, the flow is linear. Theta goes to theta plus omega. And this is represented by this picture here. We go from theta to k of theta, from theta plus omega to k of theta plus omega, and we want that f mu of k of theta is equal to k of theta plus omega. And I want to stress that this invariance equation contains two unknowns, the embedding k and the drift parameter mu. So we need to find the embedding k, like in the symplectic case, but also the drift mu in order to find the torus with frequency omega. And now we are led to the statement of the theorem, well, to a simplified statement of the theorem, which I give for conformally symplectic systems. The symplectic case was given here in this paper by De la Llave, González, Jorba, Villanueva. And it is a simplified statement in the following sense. So we start with the family F mu of conformally symplectic maps, a Diophantine frequency omega. We fix a positive parameter rho. We assume to have an approximate solution K0 mu 0, which satisfies the invariance equation with an error term is 0. We assume that this term, the error term is 0 is sufficiently small. And then we assume a non-degeneracy condition. This is a simplified statement. So this non-degeneracy condition is quite technical, so I don't want to state it here. But assume that there is this non-degeneracy condition is satisfied, then there exists an exact solution that we call K star mu star, which satisfies exactly the invariance equation, so with a 0 at the right-hand side. And beside, the true solution, K star mu star, is close to this initial one, the approximate solution K0 mu 0, in the sense that the norm, here the analytic norm, but could be also the Sobolev norm, of the difference between the two is bounded by, both in K and mu, is bounded by the norm of V0. So this is the statement of the theorem, and as it is well known, the proof of the Tkm theory is quite technical and quite long, so I don't want to give details of the proof, but just mention in a nutshell, which are the main steps. The main steps are that one starts with an approximate solution mu0 K0 with associated error term is 0. One constructs a linearization of this equation. Then one introduces a new approximation, K1 mu 1, which is obtained by K0 mu 0, so the solution at the initial step, adding some corrections, W0 sigma 0. And these corrections should be such that the new approximation, K1 mu 1, should satisfy the invariance equation, but now with an error term E1, which is orders of E0 square through that is, with the Newton's method, we go to the square of the errors of the square of the errors at the previous step. To find these corrections, W0 and sigma 0, we need to solve some cohomological equations, and this can be solved provided that we have the Diophantine condition to bound the small divisors. And indeed, to solve the cohomological equation, we need the non-degeneracy condition. Then we iterate, and beside E1, we compute E2, E3, E4, and so on, and every time taking the square of the error at the previous step. So E2 will be E0 to the 4, E3 will be 0 to the 6 and 8, and so on. And then we prove local uniqueness. So to make all these steps in an explicit way, we cannot do them by hand. We need to introduce a computer, to use a computer, and of course, to get rigorous estimates, we need to make computer-assisted proofs. Computer-assisted techniques means that we need to bound, to control the rounding off and propagation errors which are needed when we perform the expansions. And now I want to introduce two different notions of computer-assisted proofs. One is that of computer-assisted proof, which is marked in red, where one takes the computer, makes all the computations through the computers, and bound the rounding off and propagation errors using interval arithmetic, so with a rigorous control on the errors. This makes the proof computer-assisted proof, and we use this word here. On the other hand, we can have a different approach. We can have a computer-assisted validation, which are marked in blue, light blue. That is, we make the computations using the computer, but trying to have not to implement interval arithmetic, but rather implementing using a long precision, many digits, 50 digits, 100 digits computation, for example, using MPFR. So we cannot say that this is a proof, but we can say that it is a computer-assisted validation, especially if we get the same results using the 30 digits, 50 digits, 100 digits, 20 to 200 digits. So this is a short history of computer-assisted proofs. Not in general, there are many, many works, especially from different groups. For example, the Polish groups, other groups in the US, so in France and so on. And so there are in Spain and so on. But here I just want to give some results about three different examples. One is the standard map. So the other one is problems of celestial mechanics. And the third group is dissipative standard map of dissipative problems in celestial mechanics. So these are just the three groups. But once again, there are many other, fortunately, many other, Canada and so on, and many other groups working in computer-assisted proofs. So for the conservative standard map, as I said before, we started decades ago. So you see, it was this is marked 1990, but it did my master thesis was in 1984 already on these proofs. And we reached, at the time, we were able to reach 86 with Luigi, De La Llave, Rana 93, and more recently in 2016, there is a wonderful paper by Figueras Sarurluque where they give results, computer-assisted proofs for the conservative standard map up to 99.9% of the experimental value. So of the value, so 0.971635 is the experimental value, is Green's value for the standard map, and they are able to prove the theorem for 99.9% of this number. Concerning celestial mechanics, we have a spin-orbit problem. This was my PhD thesis, where I reached the 100% of the astronomical value for the spin-orbit problem for values of Moon, Mercury, and so on. Then we made several work with Luigi Cherchia for the three-body problem, again reaching 100% of the astronomical values. The astronomical value is less than the experimental value. Of course, if the objects exist, it must be so. Then let me mention also Locatelli, Giorgilli, and Sansottera for the three planets problems, and they reached 100% of the astronomical value, making computer-assisted proofs. All these are green, but now we became older and therefore lazy, and we have computer-assisted validations. So we have several digits, but we do not implement interval arithmetics. And we made recent works for the standard map and for the spin-orbit problem, in both cases obtaining 99.9% of the experimental value. Not even the astronomical. This value for the spin-orbit problem is much bigger than the astronomical value. So the rest of this talk will concern this last line, that is the estimates that can be obtained for the dissipative spin-orbit problem. Before going to this example, let me mention that the a posteriori approach has been very productive because it gave rise to several results. It started in 2005 from this paper and from Raphael's book, but then we had results about local behavior near quasi-periodic solutions, partial justification of Green's method to find quasi-periodic attractors. As I was mentioning before, refined estimates for different systems, analyticity domains, whisker tori, and it is used to construct, even in space dynamics, to construct invariant manifolds. And here I will mention the spin-orbit problem with tidal torque. So it will be a conformally symplectic system. And I want to mention that the spin-orbit problem is just one example of a conformally symplectic system. There are many other applications of conformally symplectic systems. For example, Hamiltonian chains with energy dissipations, as in the way the works by Wayne, Ekman, and Kuhn and others, Gaussian thermostats, exponentially discounted systems, Euler-Lagrange equations of exponentially discounted systems. So there are several examples where one can find applications of conformally symplectic systems. But now, in the last part of my presentation, I will be concerned with the dissipative spin-orbit problem. So let me introduce it in the following way. We have a satellite, for example, the moon, which moves the central planet, the Earth. We assume that the satellite is triaxial with principal moments of inertia I1, I2, I3, ordered in this way, and with the center of mass moving on a Keplerian orbit around the Earth, and with the spin axis perpendicular to the orbit plane. So we disregard the angle of the spin axis, as you see, now there is an angle with an orbit normal. And finally, we assume that the spin axis coincides with the shortest physical axis, and we will include also the tidal torque, which is due to the non-rigidity of the satellite, and which is a very important element to understand the evolutionary history of satellites. And here we have Silvio Ferrasmello, who is a worldwide expert in tidal theory. So apologize, Silvio, but I will deal with the most simple expression for tidal torque. Just to give an example of this problem, the spin orbit problem with tidal effects. And we know that the spin orbit problem is the most simpler example. I used it several times in different contexts, converse Tkm theory and the Nekoroshev theorem and so on. So there's different settings because it is a very simple problem. And nevertheless, it has a some physical, even if simplified, it has a physical meaning. And precisely, we know that a spin orbit resonance occurs whenever there is a commensurability between the period of revolution of the satellite with the period of rotation. So if we had that this ratio of the period of revolution over the period of rotation is equal to a fractional number P over Q, a rational number P over Q, then we have a spin orbit resonance. And it means that during Q revolutions about the central planet, the satellite makes P rotations. In the case of the moon, we have a one-to-one resonance because P and Q are equal to 1. The periods are the same, about 28 days. And this is the reason why the moon always points at the same face to the Earth, which is common to many other satellites in the solar system. Here is a very partial list because the list extends to many other satellites of the solar system. And the only body which is found in a spin orbit resonance, but not one-to-one, is Mercury, which is trapped within a precision of 10 to the minus 4 in a 3-to-2 resonance, which means that during 2 revolutions about the Sun, Mercury makes 3 rotations about the spin axis. And then we will add, as I said before, tidal effects. But first, let me introduce the equation of motion under the assumption that I was saying before, but retaining first the conservative case. So we disregard tidal torques, and we write the conservative equations of motion of the spin orbit problem as this second order differential equation. In the variable x is the angle between which gives the rotation, the angle of rotation of the satellite. And it says that x double dot plus epsilon is a parameter which is related to the equatorial flattening of the body, times the semi-major axis over the Keplerian radius of the orbit to the power 3, sine of 2x minus 2 times the true anomaly is equal to 0. So this is a very simple equation. Indeed, it is associated to a one-dimensional, time-dependent Hamiltonian. This is an important point. The conservative case corresponds to Hamilton's equations of h of y, x, and t, which is a pendulum, y squared over 2, plus epsilon times a perturbing function, and which is integrable for epsilon equal to 0. Indeed, it is also integrable for eccentricity equal to 0. Now, we add the tidal torque. So we replace the right-hand side with a function which will be a linear function of the velocity. And we will see in a moment that this system is conformally symplectic with symplectic matrix, which is the standard one, 0, 1, minus 1, 0. So what is the expression for this function TD? It is given here. It was introduced by several authors. I used, for example, the paper by, nice paper by Peel. There were papers also by Goldreich and other people, and it is given by this formula here. Minus eta, eta is a constant which depends upon the rigidity, Llave number, the density of the body, and so on. A over R to the 6 x dot minus f dot of t. And you see that this tidal torque depends also on the time. Eventually, we can also take a simplified model by taking the average over the tidal torque over one orbital period, and we obtain just a function of the velocity minus this function here, eta L bar, depending just on the eccentricity, x dot minus n bar over L bar of V. So it is x dot minus mu. Mu here is the drift, and you see that the drift is indeed replaced. The role of the drift is indeed placed by the eccentricity. So to find the right tori, one needs to tune the eccentricity in this spin orbit problem in order to find invariant tori. So going into more details about the spin orbit project with Rafael Renato and J.Gimeno, who was postdoc in Roma, and now it is postdoc in Georgia Tech through a Spanish fellowship. We made 3 different steps, 3 different works. In the first part, we worked on a reduction of the spin orbit problem to a suitable conformally symplectic Poincare map, which provides us a tool to construct a numerically the invariant tori. Then we implemented Km estimates for the dissipative spin orbit problem. And we are just finishing a third part on the computation of the experimental breakdown threshold, and this part, and there will be probably also a fourth part on renormalization theory for this problem. So what about the spin orbit map? The spin orbit map means that we take the spin orbit equation with a tidal torque depending on the time and on the velocity. So we do not average the tidal torque. We compute the map at times 2 pi. We obtain a map PE with 2 components, PE1, P2, which is indeed conformally symplectic. So it satisfies the role or the drift, as I said before, is replaced by the eccentricity. And the map PE satisfies that PE star omega is equal to lambda omega, where we can give to lambda this expression here. So it will be an exponential function. And then we can implement the theorem. We can use the theorem, Km theory, and to provide an explicit algorithm. And these are the main steps. I don't want to go into the details. I would just want to tell you that there are 13 steps which are needed to implement, possibly on a computer, in order to start to find a new approximation, K prime and E prime, so the new embedding and the new drift, if we start with an embedding K and the drift E, we satisfy the functional equation with the given error. And this new expression here will satisfy the invariance equation with an error which is quadratically smaller. How can we obtain the new approximation? Well, by computing the K and then this quantity, this quantity, this quantity, by solving the cohomological equation, which means to solve this equation here. By the way, we have here 2 unknowns, W2, the corrections W2 and sigma to the drift and the embedding, which are multiplied by matrix. And we will need that the determinant of the matrix, of this matrix here, is different from 0. And this is the non-degeneracy condition that I was keeping in the statement of the theorem. This is the non-degeneracy condition. The determinant of this matrix here should be different from 0 so that we are able to find the new solution. Okay, besides these technicalities, let me say that we can implement the theorem and we can construct numerically the tori. So we implement everything on a computer. We take, let us see at the plot here on the right. This is for omega 2 equal to the golden ratio, square root of 5 plus 1 over 2. The violet line corresponds to an epsilon very small, 10 to the minus 4. Then we increase epsilon, and we see that it is more and more distorted, and the yellow one is for epsilon equal to 1.15 10 to the minus 2. And here we plot also we show also the value of the drift, the eccentricity. So we can construct the tori. We can construct the tori, and in the same way we can try to find also the Km tori to prove the existence or give a computer-assisted validation of the tori. So this is a result in the conservative case. As I was saying before, I was at the time of my PhD thesis, I was looking at the conservative spin-orbit problem, and I proved through a computer-assisted proof the existence of invariant tori bounding the motion of the moon or other satellites on the solar system from above and below. And being the Hamiltonian three-dimensional, as I was saying before, it depends on y, x, and t. The two-dimensional invariant tori trap the motion and provide a strong stability property in the sense of confinement of the motion. So that was the result in the conservative case. And then let me say that in the dissipative case, again, the work with Raphael, Renata, and Joan, we used the spin-orbit map of the first paper, of the first part. We implemented the Km theory using making a explicit computation through a computer-assisted validation. And we are able to say that having fixed the dissipation, for example, eta equal to 10 to the minus 3, or you can use another dissipation as well, for given parameter values, epsilon equal to 0.116 for the golden ratio. We have also results for another number. There exists an invariant torus with frequency equal to this frequency here, the golden ratio, and for epsilon equal to this number. These words are crossed. They are crossed because this number here is indeed very, very close to the experimental value, as I'm going to show in the next slide. This slide shows the third part, which is the ongoing project, again with Raphael, Renata, and Joan, which uses the Sobolev norms and uses a side result of the Km theory. Because the Km theory tells us that if the torus exists, the Sobolev norms of the embedding should be regular. And when we approach the breakdown, one has a blow up of these Sobolev norms, of a trigonometric approximation of the embedding. So what we do is we take the first part and we compute explicitly the embedding. We take a trigonometric approximation, so a finite series, Fourier series for the embedding. We compute the Sobolev norm of the embedding, and when we see that there is a blow up, we mark the experimental threshold, the experimental breakdown threshold. For the golden ratio, it is given here, this number here, 0.116329. For the other number is this one. Again, eta equal to 10 to the minus 3. And the digits which are given in red are indeed the digits for which we were able to give the computer-assisted validation using the theorem and implementing explicitly the Km estimates. So what we obtain is a result which is 99.9% consistent with the experimental value. Let me also say that we could have implemented also other methods like a Green's criterion, but here we found several problems because it is in dissipative systems, it is quite difficult to find periodic orbits, and therefore we had to rely better on this Sobolev criterion. Okay, so these are the main results, and I think I'm close to the 50 minutes of my talk, so let me go to the conclusions. And the conclusion is that, well, first of all, that Km theory can give very efficient estimates, explicit algorithms, which provide a tool to construct invariant tori. One can also use similar methods to construct not only the invariant tori, the rotational invariant tori that were given in this talk, but also whiskered tori. Of course, we just looked now at conformally symplectic systems, but we think that it could be very nice in the future to look at different kinds of dissipative systems, not only conformally symplectic systems. And of course, many of these results, either rotational tori, whiskered tori, conformally symplectic, or other dissipative systems, can find, as I was mentioning before, many applications in celestial mechanics and astrodynamics, and this will be next step in the near future. So I thank you very much for your attention, and I stop by showing the 3 papers to which this talk refers. Thank you very much.
Let's thank the talk. Thank you, Alessandra, for the wonderful talk. And we have time for questions, comments.
Okay, can I ask a question?
Yes.
Hello? Can you hear me?
Yes, yes.
Yes.
Okay, there's a lot of echo. Okay, now it's better. So how likely when you have a dissipative system that your attractor actually is invariant torus? So is it more likely to have invariant torus as an attractor or some other strange attractors?
I cannot hear you, sorry. Can you speak louder?
Okay, in a dissipative system, how likely it is to have a invariant torus as an attractor instead of a strange attractor?
Yes. Well, this depends on the parameters of the system. The parameters of the system, as I said before, are the dissipative constant lambda and the perturbing parameter epsilon.
Right.
So, okay, so you have to tune both parameters in order to have a quasi-periodic tori, because if you increase very much, for example, the epsilon, or if you increase if you decrease the lambda, so you let me say in the right way, because assume, for example, to have the standard map, okay, so which is the simpler problem. So in that case, lambda equal to 1 is the symplectic case. So if you are going to lambda equal to 1, which is the symplectic limit, which is extremely interesting, and with that we analyzed with Rafael and Renato in a companion paper, you are more and more plenty of rotational invariant attractors. And if you are far from the the conservative regime, it is more likely to find strange attractors.
Right.
So you have to tune the to look at the values of the parameters in order to see whether there are invariant attractors or not. But definitely, if you are closer to the conservative limit, then you have more invariant rotational Km invariant attractors.
So in real applications, that when you have a embodied system in real solar system, for example, that is it more likely to have invariant torus or just some periodic attractors?
Well, again, depends on the values on the systems. I cannot give a definite answer. It depends on the values of the systems. Definitely, periodic orbits in dissipative systems can coexist. Yeah. And this is an important point. While periodic attractors, you have just one value of the parameter. Okay? There is a paper, for example, a nice paper, which is more than 100 coexisting periodic orbits in a standard map system. It was the 80s. In the solar system, of course, I would rather say that again, it depends. Really depends on the system that you're looking at. But definitely, if you have a dissipative system, you can use the existence of invariant tori to have information on the evolution of the systems. Look, for example, at one of the examples that we learned from Silvio, which is the Laplace resonance. The Laplace resonance was probably driven by tidal forces. So this is the meaning of the study of these dissipative systems.
Right. So I suppose it's much easier to use the Bayesian attraction to verify those attractor.
Sure.
But I guess it's hard to verify the attractor is actually a invariant torus.
Yes. Yes.
So basically,
definitely.
your algorithm, your computation is to verify that for certain dissipation and for certain frequency, you actually have an invariant torus.
And for certain drift parameter also.
Yeah, for certain drift parameter and for the dissipation, but basically the two parameters. So the two parameters has to be extremely aligned, has to be extremely sharp so that you have a attractor. If you violate any tiny bit, then the quasi-periodic attractor is gone.
Correct. Yes.
So in real life, it does not happen. Basically.
No, in real life it happens, but because, for example, in the case of the spin-orbit problem, you have the eccentricity is your drift parameter.
Right.
And if you tune properly the eccentricity, you reach a stable state where you can have a quasi-periodic attractor. So the system can, but usually I would say that this is from the celestial mechanics point of view, not from the dynamical system point of view. I would rather say that this is an evolutionary scenario.
Okay.
In the sense that you let evolve, for example, the drift parameter.
Okay.
In such a way that you reach the value at which you can have the tori.
Yeah, I understand. So if you have a one parameter family that during our evolution, so they're at one moment of time, so you have a attracting invariant torus.
Correct. Yes.
Okay. Yeah. Now I understand. Thank you very much.
Renato.
Yes, well, Alessandra, thanks a lot for the talk. I just wanted to make a small comment. I mean, of course, you will correct me if I'm wrong, but just I wanted to mention that in 2013 we also proved that these quasi-periodic attractors are normally hyperbolic invariant manifolds with fixed diagonal exponents. So going back to Jeff's question, so these are persistent. So it is true that you can only prove the existence of quasi-periodic attractors on a line, let's say, in the drift parameter space, right? But, I mean, you have as an invariant manifold, this is normally hyperbolic. So you have persistence, right? So this is the object as a quasi-periodic torus exists for, let's say, just a line, but for normal hyperbolicity, well, you have objects which are significant, let's say, for the physical systems. Well, anyway, so that's you have normal hyperbolicity, so this is really significant. That's what I wanted to say.
Yeah, thank you, Renato. But in any case, you have to tune properly the drift, otherwise you don't find the invariant torus.
Yes, I agree. Yeah.
So basically, it's Chancelier's the original idea that in the existence of invariant torus, so starting from Alain Chancelier, basically that the structure, the mechanism. Yeah. Okay.
Mm-hmm.
Okay, more questions?
So I'm quite surprised that you can get 100% your computer assisted verification or computer assisted proof can get really as close to the practical values in a numerical experiment. That's quite amazing that you can get so precise that yeah. So, but is a lot of computations. So, in terms of a computer-assisted proof, that does the verification process takes a very large computations.
Well, not really. So let me first say that we have also another paper on the standard map, on the dissipative standard map, and again, also in that case, the dissipative standard map, we have 99.9%. And there was also the paper by Luque, Figueras, and Haro, 99.9%. So this means that this kind of KM approach, the posterior approach, can really give results which are extremely close to reality, so to the experimental value. Concerning the computation, well, as I was saying, we were lazy. That is, we didn't implement interval arithmetics. Interval arithmetics means to spend a lot of time to make your program with intervals, and I was doing that during my PhD thesis, but well, it takes months. It takes months or years for one example, and to find it. Then we decided to make a computer-assisted validation that is okay. The result is obtained for 30 digits, 50 digits, 100 digits. Well, it's already enough for us.
But
then we
if
wait.
If you use interval algorithm, why do you have to have 30 digits? You don't need to have that high number of digits, right? If you use an interval.
Well, yes, indeed, I was using quadruple precision for using interval arithmetic, and this is enough. So
yeah,
and it will be enough. This is correct. But the problem is that with interval arithmetics, the computer time increases by a factor between I don't know, 5 or 6 or 7 times, and especially the time that you spend to make the program computer assisted with interval arithmetics, it's a long time. Unfortunately, we discussed some time ago in Canada, there is a special seminar on computer assisted proofs, and we discussed also about the need to have some automatic tool, automatic language that could give results, computer-assisted proofs. But this is very difficult, and that would require a dedicated project, of course. Concerning the execution time, Renato, please remind me. I think that a few hours, maybe one day of computer time, we go through the results for the spin orbit problem or the standard map, no more. So. If you want to
the order of 8 hours.
How many?
8 hours, 10 hours.
8 hours.
For one...
8 hours or so. Yeah. If you want 99.9, if you're happy with the smaller value, then it is also a few minutes.
I have some questions. In the case of the standard map, when in the symplectic case, the last torus has an important rule that it's the last torus that you have that allows the transport of trajectories. In this case, is it clear that the role played by this cantorus or not? For example, what's the important role played by them? They are important in the sense that they are separatists or attractors, in the sense that you have information about the stability of these objects and the role played by them in the phase-phase?
Well, also in the dissipative case, if you have an invariant attractor, you have that there is a confinement of the motion, as I was saying before, not between invariant tori, but in one of the two regions of the tori. Okay, so okay. This is one point. You don't have again, you cannot have a trapping of the invariant tori between two tori. Concerning the breakdown of the tori, there is there is at the breakdown, there is a nice work by Renato and Figueras. I think it was 2016, which explains the breakdown of the tori through a collision bundle mechanism between the stable and tangent spaces. And then the third thing that you were mentioning was concerning what happens when you are far from just after the breakdown, if we can have cantori. This is an interesting question. The only answer that I can give you for the moment is that the answer is positive, at least in one example, which I made with Massimiliano Guzzo some years ago, which are the existence of cantori in the dissipative sawtooth map. You know, the conservative sawtooth map, the Devil's Staircase, has explicit expressions for the cantori, and one can give also, one can modify the map and give explicit expressions of cantori for the dissipative case. We did also we tried to find also inverse Km theory, that is the converse Km theory, to provide the regions of non-existence of cantori, of invariant tori, regions of existence in the invariant tori. It was again I did a paper with Robert Mackay for the spin orbit problem. So there are, I mean, similar theories can be extended also to dissipative problems. Of course, there are many other question marks that are left for dissipative systems, and well, this is the situation for the moment from our group.
Thank you very much. Some more questions or comments? Alessandra, a general question about the drift parameter is also evident, which is the good options for drift parameters or not? In general case, I imagine a dynamical system in general, and you need to recognize a drift parameter in this case.
Sorry, the question is how to find the value, or how to find the existence of a drift parameter in a specific example?
How to find the drift parameter, how to recognize which is a good drift parameter,
okay.
if it is the case.
Very nice question, because it is not so simple, I must say. It is not simple because the examples in which you have an explicit expression for the drift parameter, at least in celestial mechanics, are not much. And the spin orbit problem, or the spin orbit problem with if insert obliquity and so on, it is one example where there is a very well identified drift parameter. But for example, if you take the Poynting-Robertson or Stokes drag, there is no drift parameter. The drift parameter is 0. Or if you take, for example, let me give a simple example, a satellite problem. You have a satellite problem in the satellite at low altitude, below 2,000 kilometers of altitude. So you are within the atmosphere. And so your satellite feels the atmospheric drag. So there is a dissipation. And you can give a form to this dissipation, and the dissipation is depending on the velocity. So the system is conformally symplectic, but there is no drift. And this corresponds to what happens in reality. If you leave a satellite in the atmosphere and you leave it there, it will fall down on the Earth because there is no drift. Okay, so in that case, the drift parameter is 0. you have to make to insert an artificial drift in that case in order to stabilize your satellite at a given altitude. It is quite difficult to find which are good examples. Solar sails might be a good example if you insert some extra parameters due to the nature of the sail or something like that, for example. But it is difficult to find physical examples, at least in celestial mechanics, where you have a non-zero and well identified drift parameter.
Okay. And a personal curiosity, in the case that you don't have dissipation, but you have a system that is no longer Hamiltonian, but is still conservative, what do you expect about Ken torus? You expect that they will remain in the phase space? It does not depend if it, for example, specifically in solar sails, in the three-body problem, in some attitude of the sail, you have a system that is not Hamiltonian, but is still conservative.
Correct.
What do you expect about the families of tor or tori and whisker tori, all that? Do you have some information about that?
Well, in that case is not conformally symplectic, so our theorem does not apply.
I see.
I never studied. I must say that I never studied these systems, and as I said before in my conclusions, that was one of the bullet points that needs to be done. That is to find to have a deeper investigation of other kinds of dissipative systems and also Tkm theory in this kind of systems. So I cannot give an answer now, and I don't have the theory for them. But there is plenty of systems like this. So with alternating energy, for example, which is not conservative, neither conformally symplectic. So
yeah, thank you very much. Some more questions or comments? Okay, if not, we can now thanks the speaker again.
Thank you very much. Thank you.
Some information, Annette?
I will start to record it, so if you want to open your cameras to take the picture from today,